Also, I have talked about observational seismology as locating earthquake and also about the curve of records in during the earthquake occurring uh, as amplitude per time or acceleration per times recording, also velocity per times recording, how locating how locating earthquakes with a trias station I have talked before, and determinations the magnitude of earthquake with a richer magnitude scales and Mercalli scales intensity. I have talked before definition intensity, what is the intensity and what is the magnitude definitions. Uh, how about magnitude determinations? In this slide, this slide shows the m0 as a magnitude, the seismic moment m0 in the equation shows m0 equal g times a times d. G is a shear modulus, a equal L times W as shown in the schematic shapes. L is the horizontal distance of area. W is vertical distance area of face on the fault plan as show the fault plan in schematic shapes. D is the average co-seismic slip. It may be calculated from the amplitude spectra of the seismic wave. Also, I have talked before about the intensity scale. The intensity scale, often referred to the Mercalli scale, qualifies the effects of earthquake on the Earth's surface, humans, object of nature, and a man-made structure on the scale of 1 through 12 scale, as shows in the table efforts as Mercalli scales between 12 scale. Also, this figures show the collapse of the buildings as a function of intensity of shaking as a percentage of building collapsed per modified Mercalli intensity. Earthquake magnitude, earliest measure of earthquake size, as the dimensionless of number measure various way, including this equation. We can use this earliest equation to measure magnitude, as shows in this slide. As a definition, the ML is a local magnitude, MB uh, is body wave magnitude, MS is surface wave magnitude, called MW called the moment magnitude. no easy for measure can use uh, this equation as shown in this slide as general formal magnitude scales. M equal in this equation as shown, M is equal log base 10 A per T plus F H delta plus C. A is the amplitude of the signal. T is its dominant periods. F is a correction. F is correction for the variations of amplitude with the earthquake depth H and distance delta from the seismometer. Meter. C is a rotational scale factor as shown. You can see in the curves, schematic curves, as the P and S recording wave show the amplitude of P and S waves per times, and the biggest amplitude as shown in this curve is 23 millimeter. This no direct tie to a physical of faults as shown, just use the as a curve recording of P and S wave. In another slide also shows the schematic shape shows the magnitude and amplitude of vibrations wave as schematic as recording with seismograph. Also, Richard notices that the vertical offset between every two curves is independent of the distance. Thus, one can measure the magnitude of the given event with respect to the magnitude of our reference event as shown the equations in this slide. ML equal logarithm base 10 a delta minus logarithm base 10 a 0 delta as shown in this slides for three event distance where a0 is the amplitude of the reference event and delta is the epicentral distance. Richard arbitrarily chose a magnitude 0 event to be an earthquake that would show a maximum combined horizontal displacement of 1 micro micrometer on a seismogram record using Wood Anderson torsion seismometer around 300 kilometers from the earthquake epicenter. But the problems with the Richard magnitude scale is the Wood-Anderson seismograph is no longer in use and cannot record magnitudes greater than 6.8. Also, for local scale for South California, and therefore difficult to compare with other regions. And just that's Richard magnitude scale based off the South California, and so difficult to compare with other regions. Another formula for magnitude calculations, as shown in this slide, another equations to measure magnitude. M is log base 10a plus c1 log dig plus c2, where a is the amplitude of ground motions, d is the epicentral distance, and c1, c2 are constants. There are many types of magnitude in uh, seismological practice, depending which waves are used to measure the amplitude, as ML, MB, MC, MS, MW call. Increase of one magnitude unit 32 times more realize seismic energy. In next slide shows the table of observational seismology, some statistical uh, numbers for example. In this table, in columns 1 show the magnitude 0 to 9 scales, and columns 2 show the effects of the magnitude scale, and column 3 in this table shows the number per year the occurring these uh, earthquakes. For example, for less than 2 magnitude scale, not felt by human, recorded by instruments only, that's so the magnitude, the less magnitude scales, and number per year can occur. So many of these scales earthquakes, but for magnitude scale between 8 to 9, the effect is complete devastations, ground waves, and the number per year can occur around 2 number can occur per year. Another table shows the another observational seismology measures, some statistics. In columns 1 show equivalence magnitude scales, columns to show the events, and column 3 shows the equivalent energy per tons TNT. For example, for equivalent magnitude 2 scale 2 event, large quarry blast, this equivalence energy is equal 1 tons TNT energy blast. And for magnitude 9.5, this occurred Chilean earthquake 1960. This equivalents around 32 billion tons TNT energy equivalence, as shown in for scale 3.5, as shown in this table. This event large lightning bolts as equivalent as same large lightning bolt around equivalence energy 75 TNT, tons TNT energy. Another table shows the 10 largest earthquake in the world science in 1900 as observational seismology statistics that show 10 largest earthquake in the world since 1900. In column 1 show location occurring this earthquake, columns 2 dates, columns 3 magnitude of that earthquake, and columns 4 shows the numbers of that durations in this earthquake. The largest earthquakes occurring in the world since 1900 was in Chile on 22 May 1960. The magnitude scale was around 9.5, and during this earthquake, around 5,000 people died. And second one occurred in the Alaska on 28 March 1964 with magnitude 9.2 and around 131 people died. And that's in third one, so a little familiar for you. And that's occurred in Russia on 4 November 1952. The magnitude was 9 and nobody dead. Etc. in level 10 occurred in Indonesia on 1 February 1938 with magnitude 8.5 and nobody dead. First one Chile, second one Alaska, third one Russia, fourth Ecuador, fifth Alaska, sixth Coral Islands, and seventh Alaska, eight India, Chile 9, and 10 Indonesia occurred. That's 10 largest earthquake in the world occurred since 1900. Next slide show 10 words earthquake causing the largest number of fatalities. Show that's occurred in China, Syria, China, Azerbaijan, and Shaanxi, China, Nangxia, China, and Homs, Iran, Kanto, Japan, Aleppo, Syria, and Messina, Italy. Italy occurred. Column 1 shows the locations and data columns 2 and the number of deaths shows in columns 3rd and columns 4 show the magnitude of the earthquakes. Next slide shows the curves, schematic curve of log n per ml. The stone solno frequencies. That shows in this slide. Gutenberg frequency magnitude relations with equations log n equal a minus bm. B is approximately constant, b equal 1 in the worldwide. There are around 10 more times m equal 5 than m times 6 earthquakes equal 6 earthquakes. This shows self similarity and fractal nature of earthquakes. In fact, macroseismology deals with effects of earthquakes on human, animals, objects, and surroundings. The data are collected by field trips into the shaking area and or by questionnaires sent there and then calculated. Also show with aesthetics, some aesthetics seismology in the tables. The effects are then expressed as earthquake intensity at age of the studies places. Intensity is graded according to macro seismic scales. Mercalli, Kunkel, Seeberg that show with MCS standard. Medvedev, Sponhor, Karnik that show with MSK standard. Modified Mercalli showed with MM or European macro seismic scale that show with EMS standard. This is a subjective methods and some standard for the measure the intensity graded according the macro seismic scales with different standards in different countries. For example, this slide shows the European macro seismic scales EMS 98 in 12 level. This slide show level 1 to 7 EMS scale magnitude. Next slide shows 6 to 12 EMS standard and shows the definitions in column 2 and column 3 show in short descriptions each level that's occur in durations and this scale of earthquake. For example, in level 5 EMS, the level 5 is so strong. The earthquake is felt indoors by most, outdoors by few. Many sleeping people awake. A few run outdoor buildings tremble throughout, hanging objects saving considerably. China and glasses clatter together. The vibration is a strong, top heavy object toppled over doors and window, serving open or shut. The descriptions of these levels can occur during the scale 5, level 5 EMS. Or in level 12 scale of EMS, completely devastating, and as description this level particular all structure above and below ground are heavily damaged or destroyed. Result of macro seismic surveys are presented on isoseismal maps as shows in this slide as schematic maps. Isoseismal are curve connecting the places with some intensities. As you can see in this slide one of isoseismal map. Do not confuse intensity and magnitude. Just approximately epicentral intensity is I0 equal m plus 2 that show the relations between epicentral intensity and magnitude equations. One earthquake has just one magnitude but many intensities. This comparison between intensity and magnitude parameter. Another branch of seismology is engineer seismology. Engineer seismology, in fact, provide civil engineering engineers parameters they need in order to construct seismically safe and sound structures. Engineering seismology is a bridge between seismology and earthquake engineering. And also, earthquakes are the only nature disasters that are mostly harmless to humans. The only danger comes from buildings designed not to withstand the largest possible earthquake in the area. Most common parameters input uh, for engineer are maximum expected horizontal ground acceleration show with PGA. Also in engineer seismology, we need for design PGV, PGD, SA, IMX. The maximum expected horizontal ground acceleration show with PGA, maximal expected horizontal ground velocity show with PGV, maximal expected horizontal ground displacement show PGD, and response spectra show with SA, maximal expected intensity show with I max. Duration of also significant shaking, dominant period of shaking also so important for engineer for design. In fact, engineering seismologists mostly use record of ground acceleration obtained by strong motions, accelerographs. Also, you can see the accelerogram of the stone Solano as Croatia with magnitude 6 that occurred in 1996. This slide show the curve of magnitude per time, also acceleration per time, also velocity of the wave per times in three curves: acceleration, velocity, and magnitude per times. In order to estimate the parameters, seismologists need first complete earthquake catalog that extend well into the past information. Second, information on the soil structure and properties at the construction site, as well as on the path between epicenter and the site. Also, record of strength earthquakes and small event from nearby epicentral regions also then should and needed the result of geological surveys. After complete the information and gathering the information about the uh, earthquakes with the seismologists and estimate the parameters, then complete and homogeneous earthquake catalogs are of paramount importance in seismic hazard studies, and then can show with some seismo city maps of criteria after the Croatian earthquake catalog that list also as for example show in this map as schematic maps, and that show the list of 50,000 events seismo city of criteria of the Croatian earthquake catalog. In estimating the parameters, you may use the probabilistic approach or deterministic approach, or combine probabilistic approach and deterministic approach. In probabilistic approach, use a statistical method to access probability of exceeding a predefined level of ground motion in some time period as the earthquake return period based on the earthquake history and geological data. And in deterministic approach, use a predefined earthquake and calculates calculate its effect and parameters of seismic forces on the construction site. This is very difficult to do because the site is and the near fields as close to the fault, and most of the approximations you normally use are not valid. Also, and maybe use a combination of two of probabilistic approach and deterministic approach. In this slide shows the example of probabilistic hazard assessment in criteria as show with the color contouring graph with coloring in PGA in duration 250 years. Also PGA per G% in 475 years. Also another one shows in 1900 years PGA as coloring contouring show earthquake hazard in southern Kotaria or Dalmatia in terms of PGA for 4 return periods. Probability of exceeds intensity in level 7 MSK in any 50-year Zagreb area also shows in the left side down of a slide as a color contouring PGA shows, for example. Next slide shows the soil amplification. In left side, show in this slide show a spectral amplification line of profile in this Slansky grace and with coloring contours in radial and transverse and vertical per frequency per distance as shown in this slide. Amplification of seismic wave in shallow soil deposit may cause extensive damage even for away from the epicenter. It depends on thickness of soil above the base rock, density and elastic properties of soil, frequency of shaking, and depend of the strength of earthquakes. Physical seismology is another branch of seismology, and then describe and explain about the physical of the seismology or knowledge about the structure of the earthquake deeper than several kilometers was gained almost closely using seismological methods. Seismologists use seismic rays to look into the interior of the earth in the same way doctors use X-ray. That shows, for example, in schematic shapes in this slide. Also, in next slide show physical seismology interior of Earth with some curves. Seismic waves get reflected and converted on many discontinuities with the earth thus forming numerous seismic phases. The rays also bend because the velocity of elastic wave change with depth in two types, body waves and maybe surface wave. Body waves, as mentioned before, P wave, S wave, also surface wave, low wave, and rail waves. About the forward problem of physical seismology, give the distribution of velocity, density, and attention coefficient with depth and position of all these continuities, calculate travel times and amplitude of some seismic phases, PP and SKS, so difficult and maybe problems. This is relatively all easy and always gives unique solutions. Given the arrival times and amplitude of several seismic phases on a number of station complete distributions of velocity, density, and attenuations, coefficient with depth and deposit of all these continuities. That's maybe inverse problem. This is very difficult and often does not give a unique solution. Instead, a range of solution is offered each with its own probability of being correct. The station is better the more data we have. And tomography. Seismic tomography gives us 3D or 2D image of shallow and deep structure in the earth as shown in this schematic shapes in 2D coloring contour show per distance per times. They may be obtained using earthquake data or explosion as controlled source seismology. These methods are also widely used in explosional geophysics in prospecting for oil and ore deposits. You can see 2D seismic topography with color contouring of distance where times. Also another tomography, color contouring as S wave speed, heterogeneity, or a structure of the base of Earth mantles. Next slide, some basic theoretical background about seismology. The theoretical seismology starts with the elements of theory of elasticity. Infinity small strain tensor has elements E that are linear function of spatial derivatives of displacement components u show with u as shown in this equation EAG equal 1 per 2 round uj per round xj plus round uj per round xi. Stress tensor has 9 elements as tau 1 1 2 etc. tau 3 3 as shown in this slide. Strain stress shear stress tensors and consists of normal T11, tau 22, tau 33, and shear stress component TIG is shear that acts on the smallest surface with the normal along height coordinates. And the fourth component is direct in the J direction, as shown in this stress tensor, shear stress tensor with 9 elements. Tau 1 1, tau 1 2, tau 1 3, tau 1, tau 2 1, tau 2 2, and tau 2 3, tau 3 1, tau 3 2, tau 3 2. Stress and strain are related by Hooke's law, as shown in this equation series. Tau ig equal sigma kl CIJKL times EKL. CIJKL are elastic constant. Considering that all internal and external forces must be in equilibrium, Newton law give us equations of motion as shown in this slide. Rho power 2 ui per rho 2 power t power 2 equal fi plus sigma j rho tau ig per round xj. I equal 1, 2, and 3. This is as shown in this slide, this is one of the basic equation of theoretical seismology, which links forces as body forces and forces or originating from stress with the body with measurable displacements. Another law combining the Hawk law equations of motion and the equation that link strains and displacement components, we obtain the Novier equations of motion in the form as shown in this slide round rho run 2 u vector per rho t power 2 equal f vector plus lambda plus 2 mu gradient times gradient u times u minus mu gradient times gradients times mu vector u vector. Here we assumed the anisotropic body, so that of all elastic constants Cijkl, only two remain and are denoted as lambda and mu. They are called Lamb's constants. This is rather complicated 3D partial differential equation describing displacement within the elastic body. This just for more information, some equations here. The Novier equation is usually solved using the Helmholtz theorem, which expresses any vector field, in our case displacement, u, as this equation u vector equal gradient phi plus gradient times psi, where phi and psi are called scalar and vector potentials. They may be shown to be directly linked with longitudinal and transversal waves, respectively, obeying wave equation. As shown, this equation gradient power 2 phi and gradient power 2 psi, as shown in this equation, and also show the alpha and beta equation. In these expressions, alpha and beta are velocity of longitudinal and transversal waves. We see that they only depend on the properties of material through which they propagate. The physical equations present are the most basic ones, combined with the general principles like conservations of energy, law of physics, and with boundary conditions that nature imposes, function of stresses of a free surface. They are fundamental building stones for all problems in theoretical seismology. Here is some highly recommended reading some references and sources you can use for study more about that equations. Some some other sources you can use for study more and its investigation. Now we are going to have some definition and descriptions about the vibrations and waves and some properties. We define the properties of waves and some parameters we use for calculate the magnitude, accelerations, uh, amplitude, and velocity of waves. Vibration and waves. First, we expressed about the general definitions of vibrations and waves. Vibration, in a general sense, anything that switches back and forth to and forth, side to side, in and out of and low and soft or up and down is vibrating. A vibration is wiggle in times. How about wave? A wiggle in both space and time is a wave. A wave extends from one place to another. These definitions of the vibrations and wave. Vibration and wave relations. The source of all waves is something that is vibrating. Waves are propagations of vibration throughout space. These relations between uh, vibration and wave and uh, that definition and descriptions about the wave and vibration. Now we are going to describe about parameters and properties of waves. What does the period T or period length of pendulum that's show with L, acceleration due to gravity show with G. In this slide shows the schematic shape of the vibrations of a pendulum, the to and fro vibratory motions in also called oscillatory motion or oscillation. You can see in this slide. Now we are going to have definitions about T, L, and F, T period, L, length of the pendulum, F, frequency, P is the period as shown with this equation as shown in this slide. T equal to P square L per G. L is the pendulum, is length of the pendulum. G is the acceleration due to gravity. P, the number of the P is trying to form. This show the vibration of a pendulum. Next slide shows the spring motion with the weight of here and shows the curve of a spring motion that when the oscillation are small, the motion is called simple harmonic motion, SHM, and can be described by a simple sinus curve as shown in this slide, and show some parameters of the wave emotion after vibrations of the spring. We have wavelength, amplitude, wavelength show with lambda is the distance between two consecutive peaks in the curve. Amplitude show with Z is the height of the wave above or below the equilibrium point, as shown in this schematic shape. The wavelength that show with lambda the distance between two consecutive peaks, and amplitude is the height of the wave above or below the equilibrium point. Also, we have wave period that show with t. This is the time it take one wave to pass the observer, as shown in this schematic shape. The wave properties period. Also, another parameters is frequency that show with f. F is the number of wave passing a particular point in 1 second. You can see the wavelength, period, and frequency per hertz in this slide. In this slide, show the displacement of wave per times after vibration. In frequency 4 Hz and 8 Hz. Example for frequency. What is the frequency of the second hand of a clock? The frequency of the second hand of a clock is 1 cycle per 60 seconds, and period is 60 seconds. Another question: what is the frequency of US presidential elections? Okay, frequency for the frequency of US presidential election is 1 election per 4 year, or period is 4 years. In symbolic form, the frequency equal 1 per t or periods. The relation between period and frequency shows in this equation. The before mentioned, as before mentioned, for body wave types, we have two types: transfer waves and longitudinal waves. In longitudinal waves, vibrate across from direction of travel. But in longitudinal waves, vibrate along the direction of travel, as in a spring, as shown in this slide. For example, in spring. Also, you can see the schematic shape of sound waves as compressions and rarefactions in this slide as schematic shape. The molecules in the air vibrate above some average position, creating the compression and rarefactions. We call the frequency of sound the pitch. Also, wave motion, speed, and time. Energy, not matter, from one place to another. A vibrating source transfer a disturbance. Speed depends on type of vibrating source and medium through which it travels. The wave speed is equal if frequency times lambda, the length of wave. The same type of wave moves at the same speed regardless of frequency and lambda. For any wave, f is inversely proportional to lambda. Next slide show the wave interference, as can two wave combine and give reinforcement or maybe give the cancellations. When two waves pass each other, their superposition cases reinforcement or cancellations. As you see in the schematic way, as a construct interference, when the crest of one wave overlaps the crest of another, the combinations of two waves give reinforcement. Their individual effects add together, resulting in wave increase in amplitude. As shown the left side waves.
You are currently the only person in this conference.
Do you have my voice? Sorry. Is my voice clear for you? Yes, of course. Okay, we continue. Okay, the destructive interference. We have combinations of two waves that give cancellation. When the crest of one wave overlaps row of another, reducing their individual effects give cancellation. For example, water waves show this best example. that give out of phase. The crest of one wave arrives at a point at the same time as a stroke of the second wave arrives. Effects cancel each other. In fact, two wave crests and throughout arrive at a place at the same time. Effect reinforce each other as shown in these schematic shapes. The superposition of two identical transverse waves in phase producing a wave of increased amplitude. Interference occurs when two sounds of different frequency are here superposed and give reinforcement. Constructive interference cases louder sound and destructive interference case fainter sound. This alternating pattern produces a best. A piano tuner listens for bass beats to these appears as destructive, constructive, and or destructive, constructive. That's you can see it in the schematic shape, sound wave interference. Also in this slide show the schematic shapes of water wave interference. The left side is theoretical drawing of an interference pattern, and right side is the actual interference pattern. A standing wave occurs when a wave reflects upon itself and interference causes the pattern. As shown in these schematic shapes, nodes remain stationary. Antinodes occur halfway between nodes. You can see when in same phase give reflected wave reinforcement, when out of phase give reflected wave as cancellations, and show reflected wave, incident wave in the schematic shape. Another one show the change the frequency in the standing wave, and more nodes or antinode appear in the events as a schematic shape. Another parameter is Doppler effect. What is the Doppler effect? Doppler effect, in fact, refers to the change in frequency when there is relative motion between an observer of wave and the source of the wave. For example, Doppler with sound. You can hear the Doppler of with the sound. This refers the change in frequency when there is relative motion between an observer of wave and the source of the wave. Example, Doppler with water. Change in frequency due to the source of receiver. Greater the speed, the source, greater the Doppler effect. You can see the schematic shape, a stationary bug and bug swarming. In frequency, redshift decrease in frequency.
Be very, very quiet.
This Doppler shift gives radial velocity and show the true velocity and then show the Doppler velocity.
Be very, very quiet. I'm hunting rabbits.
Radar and tangential velocity and true velocity show in this schematic shape. In this slideshow, compare these a spectrum of hydrogen in the lab and a spectra in the star with color contouring. This slide shows the whole pattern made overlapping crest and show the velocity less than velocity of water. Maybe another shapes, a second one show the velocity equals velocity of water, and third one show the velocity greater than velocity of water, and fourth one show the velocity much greater than velocity of water. Schematic shape show the supersonic aircraft, three-dimensional concave, and also sonic bomb, sharp crack, hard wind, shell of compressed air that sweeps behind a supersonic aircraft, reaches listener on the ground below and in the location A, B, and C. When the velocity of aircraft higher than the velocity of sound, then give the supersonic. Subsonic, in the subsonic, the velocity is slower than the speed of sound. In the supersonic, the velocity is faster than the speed of sound. Subsonic is slower than the speed of sound, and supersonic is faster than the speed of sound. Here we have the equation of Mach number. The Mach number is the ratio of speed of object per speed of sound. Maybe this object is aircraft or other instrument. Now we have the review of questions. First questions. Doubling the mass of a simple pendulum undergoing a small oscillation, does that to the period of the pendulum. A. Cuts it in half. B. Increase it by the square of 2. C. Noting. D. Doubles it. Doubles it. Which answer is correct? Answer. Noting. Next question. What dictates the frequency of a sound wave? A. Wavelength. B. Medium. C. Source of the sound. D. Speed. A. Amplitude. Which is the correct answer? Source of the sound is the frequency of a sound wave. Next, what determines the speed of a wave? A, the frequency. B, the wavelength. C, the amplitude. D, the period. E, the medium of transmission. Which one is correct answer? E, the medium of transmission. Next one. A skipper on a boat notices wave crest passing his anchor chain every 5 seconds. If the wave crests are 50 meters apart, what is the speed of the water wave in meter per second? A5, B 15, C 75, D 10, E 3. Which is the correct answer? The correct answer is 3. 50 per ratio of 50 per 5. Next one, for a medium transmitting a longitudinal wave, the areas of the medium where the density of the medium is temporarily increased are called A. Collisions. C. Density holes. Which one is correct answer? Compressions. Next questions. When you move away from a fixed sources of sound, the frequency of the sound you hear A is greater than what the source emits. B is less than what the source emits. C is the same as what the source emits, which is correct answer. B is less than what the source emits. When you move away from a fixed source of sound, the frequency of the sound you hear is less than what the source emits. The plan are produced because the plan breaks through the sound barrier when the plan reaches the speed of sound c by the plan traveling
You are currently the only person in this conference.